A quick review. So we're doing Fourier transform, of course, and Fourier transform in particular for periodic signals, right? So just to give you a quick recap, what Fourier transform is. So Fourier transform is x of j omega, which is a function of omega, integral from minus infinity to plus infinity, x of t e raised to a minus j omega t times dt. And this allows us to analyze any signal in the frequency domain. So x of j omega gives us the frequency content analysis, if you will, of the signal and the frequency decomposition, if you will, right? And so this is the forward Fourier transform. The inverse Fourier transform is if you're given the Fourier transform, you can find the corresponding time domain signal by this expression, which is called the synthesis expression. And this just says the x of t is once again made up of a superposition of complex periodic exponentials, infinitely of many of them with frequencies lying on a continuum of values on the real number line. So it's uncountably infinite number of exponentials. Then we talked about Fourier transform of periodic signals, right? So Fourier transform of periodic signals. So why would we want to? So if you can somebody highlight for me, why are we interested in Fourier transform of periodic signals, even though we've talked about Fourier series for periodic signals, right? So Fourier transform किस लिए करेंगे हम? Anyone? Right. So the reason why I want to do that is we want to provide a unified framework which can deal with both periodic signals as well as aperiodic signals, and just a single thing that we do and allows us to do that frequency content analysis for both the periodic signal as well as aperiodic signals. Right. So for that, one of the things we concluded was in the last lecture was if I take an periodic exponential e raised by j omega naught t, and then I compute the Fourier transform for that. The Fourier transform for this turns out to be 2 pi delta omega minus omega naught, right? And we went about this in an opposite fashion, in a reverse engineering, if you will. So we took this particular signal, found out the inverse Fourier transform, and indeed it turned out to be the e raised by j omega naught t. Now the question is, KG, how can we use this to determine the Fourier transform for periodic signals in general? We did an example for cosine. I'm going to now generalize this for any periodic signal. So if a periodic signal x of t is given as summation k equals minus infinity to plus infinity a k e raised to power j k omega naught t. So this is the Fourier series decomposition. Now using results 1 and results 2, what do you think the Fourier transform for x of t should be now? What should be the Fourier transform of x of t, which is in equation number 2? Can I use the result in equation number 1 to come up with a Fourier transform for equation number 2, or the signal in equation number 2? G. Abdullah.
So it will be ak multiplied by the expression 2 pi and delta.
All right, and there should be a summation as well, right?
Yes.
And why do you think that would apply? I mean, what's the reason for that? Why would the summation stay intact, if you will?
So we can see them as a different signals being adding up. So उनकी Fourier transformations भी add होगा.
Okay. So there's a linearity of the integral, Fourier integral, if you will, right? So that's a linear operation. So outside integral, so इसका मतलब ये है कि if I just multiply ak with e raised to power j omega naught t, right, k omega naught t, the Fourier transform for this is going to be 2 pi delta omega minus k omega naught, and I just multiply this with ak, right? And that's because of linearity. Because it's an integral, if you just plug in the definition, the constant can come out of the integral because the integral is a linear operator. And then if I have a summation on the left-hand side, I'll have a summation here as well, once again, because of the linearity of the integral, right? So what we conclude from here is that the periodic signal, which has a Fourier series decomposition given as the following, or the Fourier series coefficients given by AKs, the Fourier transform for that is going to be equal to x of j omega, which is equal to summation. So I can pull 2 pi out of the summation, and then this is k going from minus infinity to plus infinity, a times k delta omega minus k omega naught, right? So the Fourier transform for a periodic signal is actually a train of impulses now, right? And those impulses are actually scaled by constants, which are actually the Fourier series coefficients, right? So, I mean, this is just a way of going directly from the Fourier series decomposition to a Fourier transform, where those Fourier series coefficients are actually converted to impulses in the frequency domain, okay? And spaced omega naught radians per second apart, right? So let's do some examples for this. Some examples we've done already, but let's one example we've done already. Let's do another example, which is if x of t was equal to sine omega naught t, and I ask you to find the Fourier transform for this, right? How would you find the Fourier transform? The first thing is sine omega naught t is a periodic signal, right? And since it's a periodic signal, it is not absolutely integrable, right? It's not absolutely integrable. We know that the Fourier transform is not going to converge either, right? But we can, in this particular case, represent the Fourier transform as in the form of impulses, right? And that allows us a tool to be able to specify the Fourier transform of this periodic signal in terms of impulses. So how do I go about this? The first thing I do is I found out exactly as Daniel suggests, to find the Fourier series decomposition. And the easiest way to do that, the Fourier series decomposition, is just to use the Euler's identity, right? So this is 1 upon 2j. This is e raised to power j omega naught t minus 1 upon 2j e raised to power minus j omega naught t, right? So this is the Fourier series decomposition, okay? Ji Hassan?
Sir, can we use trigonometric Fourier series decomposition?
You अगर आप कर लें उसको, so Fourier trigonometric Fourier series decomposition अगर आप करेंगे, तो what do you think the answer would come out to be, Hassan? That's an interesting question.
That's where I'm unsure, because जब मतलब question आता है, I'm not really sure which decomposition to use.
Right. So
or
my
which will make
advice
it
would
easier.
be forget about trigonometric Fourier series.
Okay.
Right. Just apply the exponential Fourier series because that's general, that's generic, right? You don't need to worry about कि यार मैंने इस पे कौन सी वाली चीज लगानी है. I mean, exponential Fourier series applies to everything.
Okay.
Right.
Okay.
But just as a point of information, I mean, if you do apply trigonometric Fourier series decomposition, you'll get the single BK term. तो ये signal वापस इसी तरह. This is actually the trigonometric Fourier series decomposition. आपको पहले दी गई है, right? So it's already there. It's already there, right? But if you wanted to find the Fourier transform now, you would have to go into the exponential decomposition, right? Because you need complex exponentials, right? So the question now is, okay, what would be the Fourier transform for this? Right? What would be the Fourier transform for this? So this would just be 2 pi times 1 upon 2j delta omega minus omega naught and minus 2 pi 1 upon 2j delta omega plus omega naught, right? So k is just minus 1, and that therefore this becomes plus omega naught, right? And therefore this becomes equal to this is pi by j delta omega minus omega naught minus pi by j delta omega plus omega naught, right? And if I were to sketch it out, I mean, into sketching it out, I would once again have two impulses as far as the Fourier transform is going to be concerned, right? So Fourier transform, is it real or is it imaginary, by the way? Or is it complex? Right? We see it does not have any real part. Right? It does not have any real part. It's all imaginary because it's a 1 upon j there. Okay? So if this is omega and if this is 0, the impulses are going to be at omega equals omega naught, and the height is going to be a complex height which is pi by j. So this actually you could say the is an imaginary height. Okay? And excellent, as Usman suggests as well, the another pulse is going to be at minus omega naught, and the height for that is going to be minus pi by j. Okay? So mind you, I mean, this is just a visualization. I mean, so it's pi by j is the imaginary height, right? So, and minus pi by j is a negative imaginary height, right? So this is two impulses, and the impulses are scaled by a complex number, right? So this is for a sinusoid. Let's look at another periodic signal.
Excuse me, sir.
जी दानियाल.
सर ये जरा अजीब शायद क्वेश्चन होगा, लेकिन सर इनपुट सिग्नल साइन ऑफ ओमेगा नॉट टी है ना, तो बेसिकली ये एक ऑड फंक्शन है, तो इसका डीसी कंपोनेंट भी तो होना चाहिए कि नहीं?
डीसी कंपोनेंट नहीं होना चाहिए, राइट? इफ इट्स एन ऑड सिग्नल, पहली बात तो उसका कभी डीसी कंपोनेंट नहीं होगा.
ओह हाँ, सही.
But let me I mean, make a point here. Does that mean that if the signal is not odd, it will not have a DC component? Or it will have a DC component? I mean, are they?
So not
necessarily, right? You can
necessarily,
have a signal which is not odd, yet it has a zero DC component. And an example for that is a cosine.
Okay, sir.
Right? That's an even signal, yet it does not have a DC signal, a DC component. Okay? That's good. All right. So here's another example, which is x of t is equal to summation k going from minus infinity to plus infinity delta t minus k times capital T, where the capital T is just some time period. Okay. Do we know the Fourier series decomposition for this? And it turns out, okay, yes, we do. We've done this actually already in the tutorial. It's a solved example in the textbook as well, as people say in the chat box. So AKs are just equal to 1 upon T, regardless of what K is. So I'm not going to do the evaluation here. We've done that, right? So that means x of T is actually equal to summation. You have 1 upon T outside, K going from minus infinity to plus infinity, e raised to power j k omega naught T, right? So this is something we know, right? Usman, you say 2 pi by T, उसका क्या मतलब है?
So I was saying for x j omega.
Okay, x of j omega. All right. So let's compute x of j omega. Right? So x of j omega is going to be equal to 2 pi by T, right? And this is going to be k going from minus infinity to plus infinity, and this is delta omega minus k omega naught. Okay? And just a simple application of the things that we've done up above, right? And I could just slightly modify this as well and say, this is summation k going from minus infinity to plus infinity delta omega minus k times 2 pi upon T. All right. All right. So what does that mean? I mean, in terms of the Fourier transform, the Fourier transform or the time domain signal, if I have a time domain signal here, which is a train of impulses, right? So this is a train of impulses. This is x of t. right? So this is 0, this is t, this is 2t, and the heights are all 1, right? So if this is x of t, the Fourier transform for that is also a train of impulses in the frequency domain, right? So this is omega. I have an impulse which is at omega equals 0, and the height for that is 2 pi by t, right? The next impulse is going to be at where? Where is the next impulse going to be? T divided by 2 pi. उल्टा कर दिया दानियाल. Right, so this is going to be at 2 pi by t, right? And the height is going to be 2 pi by t as well. And here is going to be 4 pi by t and so on and so forth. Here is going to be minus 2 pi by t. This is going to be minus 4 pi by t and so on and so forth. Okay, so the Fourier transform of a train of impulses in the time domain is once again a train of impulses in the frequency domain as well, right? So if the impulses are spaced capital T seconds apart in the time domain, the impulses in the frequency domain are spaced 2 pi by t radians per second apart. Okay, and using a similar methodology, any periodic signal that you come across, you will be able to find the Fourier transform by doing what? By first of all computing the Fourier series decomposition, and from there just converting that into impulses. Okay, and this makes sense as well, by the way. When we say that periodic signals are composed of exponentials which are harmonically related, right? And this figure here exactly tells you that okay, there's no longer a continuum of frequencies which contribute to the periodic signal, but rather the frequencies that contribute are harmonically related, right? So at 0 and omega naught and 2 omega plus minus 2 omega naught plus minus 3 omega naught and so on and so forth. All of them over a discrete set, they sum up, and that's what contributes to a periodic signal. As opposed to an aperiodic signal, jahan pe we saw that there was a continuum of frequencies that contribute to the aperiodic signal. Okay? So everything clicks together. Everything makes sense. Right. Are there any questions here before I move on?
Excuse me, sir. तो पहले हमने पढ़ा था कि जब फ्रीक्वेंसी जब टाइम डोमेन में इम्पल्स होती है तो फ्रीक्वेंसी डोमेन में एक पूरी हॉरिजॉन्टल लाइन होती है, मतलब कांस्टेंट फंक्शन होता है. तो इसमें बिल्कुल सेम कॉरेस्पॉन्डेंस क्यों आ रही है? लाइक यहाँ भी इम्पल्स हैं, वहाँ भी इम्पल्स हैं.
क्योंकि देखें, अब we no longer have a single impulse, right? We have a train of impulses, right? That's the fundamental difference. If you're asking कि वहाँ पे straight line क्यों थी और यहाँ पे impulses क्यों आ गई, is there an intuitive reasoning for that? I'm not exactly off the top of my head. I mean, I may not be able to come up with that right now. Okay, what is that intuitive reasoning? The reasoning I can give you is the Fourier analysis. I mean, you go through those analysis, and that's what it turns out to be. The train of impulses in the time domain is a train of impulses in the frequency domain. Okay, Daniel, were you asking for an intuitive? Ye kyun hai? Impulses kyun hai?
Yes, sir.
Yeah. So intuitive answer सोचना पड़ेगा मुझे. Maybe I'll think about this and get back to you.
सही है.
Okay.
Thank you.
Any other questions? So Daniel, अगर आप मुझे बाद में remind भी करा दीजिएगा, perhaps on give me a direct message. Okay, this is an explanation that you require. Okay. All right. So let's move ahead and talk about properties of the continuous Fourier transform. Okay. And you see, I mean, the flow that we're following, if you will, I mean, is more or less the same that we did for the Fourier series component, right? The module, right? We developed the Fourier series analysis and synthesis, and then we talked about KG properties kya hai. And when I say properties, which were what happens if there's a time shifting in the time domain, what happens to the Fourier series components, the coefficients. If there's a scaling in the time domain, what happens to the Fourier series coefficients, and so on and so forth, right? And this is exactly what we're going to do with the Fourier transform now. It's the same kind of question that we're going to try to answer. If there's some operations that we do in the time domain, what happens in the frequency domain? And that will help us in finding out more about what the nature of the Fourier transform is. So the first property is pretty straightforward. So that's why I'm not going to spend a lot of time on it. There's just simply linearity, which we've implicitly done already, right? So if it's SKG, the first thing I want to say is KG, when I use this notation, and I've been using this quite a lot, right? This means this is the Fourier transform, right? So that means x of t and x of j omega are pairs, right? So x of j omega is the Fourier transform of x of t, and x of t is the inverse Fourier transform of x of j omega, right? So we say this exists in a pair, right? So this is the notation I'm going to keep on using. Similarly, I may, or perhaps I may not, I don't recall, let me say this now because that's there in the textbook. Another notation that's often used is x of j omega is equal to this function f, which means it's the Fourier transform of x of t, right? So this is often used as well. Another notation that you may see in the textbook is the inverse. Okay, the x of t is the inverse Fourier transform of x of j omega. So this is also a notation that you may use, right? So pretty straightforward. Right, so with the linearity, if x of j omega is the Fourier transform of x of t, and y of j omega is the Fourier transform of y of t, right? Then what is the Fourier transform of a times x of t plus b times y of t? That should be straightforward. You can prove it by plugging in the transform relationship. This turns out to be equal to a times x of j omega plus b times y of j omega, right? So there's a linearity that is inherent, right? So here's the second property, which is time shifting. So if x of t has a Fourier transform of x of j omega, the question is, okay, what is the Fourier transform of x of t minus t naught? Right, and then let's call that y of j omega, right? And so the question we want to really answer is, okay, how is y of j omega related to x of j omega, right? What is that relationship, right? Any wild guesses on what that relationship should be? Because this is very related to what we did in Fourier series analysis. Any guesses? Right, no guesses? If I would change omega to t, then make the change. Okay. Do you, Usman?
सर जब एनालिसिस इक्वेशन में e की पावर माइनस j ओमेगा t होता है तो आई गेस वहाँ पे t की जगह t माइनस t नॉट पुट कर देंगे.
Right. Okay, so sort of there. It's a multiplication by an exponential. Mehreen says a multiplication by an exponential. Why do you say that, Mehreen?
Sir, because that's how we did it in the Fourier series. So I'm assuming it might be the same.
All right. So it is in fact exactly the same, right? And the way you prove this, or the way you go about this, is exactly how we did in Fourier series. But let me do that nevertheless, right? So y of j omega is defined as the Fourier transform of this new signal, which is x of t minus t naught. And this is e raised to power minus j omega t times dt, right? And I want to relate it back to the Fourier transform of x, right? So therefore, I'll make a change of variable as we did in the Fourier series analysis as well. Let me say the tau equals t minus t naught. Then y of j omega is equal to summation, and the integral limits stay the same because they're from minus infinity to plus infinity. So, and this becomes x of tau, and this becomes e raised to power minus j omega, and small t is actually equal to tau plus t naught, right? And dt is the same as d tau because there's a shifting, right? Translation. And this therefore is equal to e raised to power minus j omega t naught times minus infinity to plus infinity. And this would be x of tau e raised to power minus j omega tau d tau. And then what you have inside this integral here is what is nothing but the Fourier transform of x, right? So therefore, y of j omega is equal to e raised to power minus j omega t naught times x of j omega. All right. And so let me write down the result here. So that says x of t minus t naught has a Fourier transform, which is equal to e raised to power minus j omega t naught times x of j omega. So shifting in the time domain only results in a multiplication of the Fourier transform with this exponential, right? With this exponential. And I can also conclude that if I compute the magnitude of y of j omega, what do you think I should get? I will get. So if I compute the magnitude of y, so this is the magnitude of e raised to power minus j omega t naught times x of j omega. What would this be equal to? Right. So why, Abdullah? Why should it be the same?
So just a guess.
Just a guess. Right. Talha says the same as well. Why the same? Talha?
Magnitude of e raised to power minus j omega t naught 1 होगा. तो
Yes.
जब x of j omega के multiply करेगा,
Yeah, so this is equal to the magnitude of e raised to power minus j omega t naught times the magnitude of x of j omega. And I know that the magnitude of e raised by j omega times t naught is actually equal to 1. Right? That's just cosine theta plus sine theta, j sine theta, and the magnitude of that is 1. Okay? So the magnitude remains unchanged. It's the phase that's actually changed, right? The phase of the complex signal, which is y, and the phase of the complex signal that is x, they are related by, how are they related therefore? Right? So if I say Kiji, what is the phase of y of j omega? How is that related to the phase of x? That's just a simple complex number analysis. That's just equal to the phase of x of j omega minus omega times t naught. Right? Is that clear? Why does that happen? Right? It's just a simple polar coordinate analysis, right? Okay, multiplying e raised by minus j omega t naught just means that you're adding some phase, which is equal to actually minus omega t naught. Okay? So the shifting in the time domain does not change the magnitudes of the exponential contributions of the exponentials, right? But only changes the phase contribution of those exponentials, right? And this would make sense as well. How? So you can think of this as a sinusoid, for example. A sinusoid hai, right? And you shift that sinusoid by some t naught. The magnitude of the sinusoid does not change. The amplitude of the sinusoid does not change, right? It is the phase of the sinusoid that changes, because the phase is actually comes about from the time shifting. Okay? So that's one intuitive interpretation of why only the phase changes in the frequencies. Okay. There was a hand raised, I think, Daniel.
जिससे मैंने वो यही कहना था कि आपको एग्जांपल दे दें, इससे मतलब कि सीरीज ऑफ जैसे हमने पहले कहा था, मैं समझ नहीं आ रही कि फेज शिफ्टिंग से क्या मुराद है, मतलब
phase shifting, you see, I mean, phase shifting, at the end of the day, what you're saying is that the time domain signal is made up of a summation of complex exponentials, right? And the Fourier transform evaluated at omega tells you what? Tells you what the magnitude of that exponential contribution is and what the phase of that exponential contribution is, right? Exponential are sinusoids, okay? In a real sinusoid and an imaginary domain में sinusoid है, तो उसका phase change हो रहा है, उसका magnitude change नहीं होता for every frequencies. Now you can in order to understand this perhaps a little bit more, I'll leave this off as an exercise and say, what if you had x of t is equal to cosine 2 pi t plus sine 4 pi t and चलें 3 sinusoid ले लेते हैं and cosine 6 pi t, right? You do a change, you do a shifting and check it, what is x of t minus t naught? X of t minus t naught is a cosine 2 pi t minus 2 pi t naught plus a sine 4 pi t minus 4 pi t naught, and there's a cosine which is 6 pi t minus 6 pi t naught, right? So the magnitudes of each one of these cosines has not changed. It's still one. It's still one here, and it's still one here. But what has changed? What has changed are these phases. This phase has changed from up above. This phase has changed from up above, and this phase has changed from up above, right? And more importantly, this change in phase is proportional to the frequency. So phase change is proportional to the frequency, right? And as I can see, यहाँ पे the phase change is 2 pi t naught. यहाँ पे it's 4 pi t naught. It's twice that, right? Because the frequency was twice that. Here it's 3 times that because the frequency was 3 times that. Okay? And this is exactly what this expression represents. Okay, the phase change is proportional to the frequency, right? So it clicks together. Everything fits together. Okay?
जी सर बेसिकली सर फ्रीक्वेंसी डोमेन में फेज शिफ्ट का मतलब ये है कि जिस तरह हम लोग टाइम डोमेन में अपने सिग्नल को राइट या लेफ्ट शिफ्ट कर रहे थे.
Yeah, something like that. Yes.
चलिए ठीक है, थैंक यू सर.
Okay. लेकिन दानियाल जो I can, so आपके frequency domain में, right? So there are multiple frequency contributions, right? If I say कि जी मैं सिर्फ एक frequency component ढूंढता हूँ, सिर्फ उसका phase change कर देता हूँ, तो फिर time domain में क्या होगा? Right? What does that? What would that mean?
सर सिग्नल चेंज हो जाएगा.
सिग्नल चेंज हो जाएगा और वो डिस्टॉर्शन आएगी, और वो किस तरह की डिस्टॉर्शन आएगी? वो आएगी कि वो जो फ्रीक्वेंसी कंपोनेंट्स जिनका फेज आपने वहां पे चेंज किया ना फ्रीक्वेंसी डोमेन में, सिर्फ उनमें टाइम शिफ्टिंग आ रही थी, बाकी सारे के सारे उधर ही खड़े हैं, बाकी सारे के सारे उधर ही खड़े हैं बाकी, और जो सिर्फ आपने चेंज किया वो सिर्फ वो शिफ्ट हो गए, राइट? सो दिस वुड नॉट बी इक्वल टू the entire signal shifting, right? So there's some components that do not shift and there are other components that shifting and causing distortion.
So basically आप कह रहे हैं डिले आ जाएगा किसी साउंड के अंदर?
Yes, phase change in the frequency domain is sort of related to a delay in the time domain.
Okay sir, ठीक है.
ठीक है, good. तलहा आपने हाथ खड़ा किया था मेरे ख्याल में.
सर ये क्वेश्चन पूछना था जो भी आपने उससे पूछा.
All right. Okay, good. All right. So Zen, do you have a question?
Yeah, sir, I wanted to ask if जो डिले आता है सर वो लाइक टाइम एडवांस वाली सेंस में आता है या फिर लाइक आगे लैग करता है लीड करता है या वो डिपेंड करता है कि वो वाली
either one of them, depending on whether the T naught is positive or negative. Right? As Daniel said, depends where you're shifting. If T naught is negative, so you're actually advancing. If T naught is positive, you're delaying.
ओमेगा के साथ किस तरह रिलेट होगा यार? What if how do we know T naught positive है या negative compared to J omega?
Right. So T naught could be anything, right? So T naught is a variable.
लेकिन अगर हमारे पास फ्रीक्वेंसी डोमेन है, हम फ्रीक्वेंसी से जब वहाँ पर एक टाइम डोमेन में लेके जा रहे हैं, तो ठीक है, पहले हम उसको कन्वर्ट करेंगे, we'll get a T naught and then we'll see it.
Yeah. Right. So I'm not exactly sure what you mean by that. Right. So
I'm asking कि अगर हम जिस तरह आपने कहा था कि फ्रीक्वेंसी डोमेन में हम अगर चेंज कर रहे हैं सिर्फ एक सिग्नल को, सिर्फ एक पार्ट को, एक फ्रीक्वेंसी को, and when we come back to time domain में सिर्फ एक सिग्नल का एक पार्ट चेंज होगा, it will be shifted.
Yeah.
तो वो पॉजिटिव शिफ्ट होगा या नेगेटिव, ये हमें किस तरह पता चलेगा? क्योंकि हमने
डिपेंड्स कि आपने वहाँ पे जो फ्रीक्वेंसी डोमेन में फेज चेंज किया था वो किस तरह चेंज किया था.
सो ये उसका प्रोपोर्शनल ही होगा, अगर हम उसको फॉरवर्ड कर रहे हैं ये भी फॉरवर्ड ही होगा.
Exactly. I mean, phase नेगेटिव करें या पॉजिटिव करें, that would make a difference. Right? I mean, there are more nuances involved, by the way. I mean, there's the concept of negative frequencies as well, which I'm sort of the effect of that, which I'm sort of glancing over. Negative frequencies may affect opposite hota hai. Right? But let's not just go too deep. Right? Intuitively speaking, phase change in the frequency domain is sort of related to time shift of those components in the time domain. Okay? Acha. So here's property number 3, I believe. Right? And this is once again related to very much similar to what we did for Fourier series, conjugation and conjugate symmetry. And I may not spend a lot of time on this because we've already done that when we talked about Fourier series. So the question here is, once again, if x of t has a Fourier transform x of j omega, let me pull this up. What is the Fourier transform of x conjugate of t? And in order to do this, so I'll just quickly go through the proof. So this is y of j omega. Y of j omega is a Fourier transform of x conjugate of t, right? So this is the definition. Now, how do I relate it to x? Now, Usman, you're almost there, but it's a slight bit of a thing that you're missing. So how do I, so if you, Usman, how do I move forward?
Yes, sir.
आगे क्या करूँ? I mean, proof करने के लिए अगर, if I ask you to prove कि जी, or find out a relationship between y of j omega and x of j omega, so what do I do?
Sir, I guess तो इसका तो फिर अगर minus j omega हो देगा, x conjugate minus j omega की जगह.
All right. Right. So there's somebody who is Mahanur.
सर आप दो दफा conjugate ले लेंगे, once over the whole integral and उसके फिर बाहर, and then you know the value of x of t.
Excellent. So this is exactly the same thing that we did with the Fourier series, right? Zabardast, right? So I would rather say कि let's take the conjugate on both sides. चलिए ऐसा कर लेते हैं. So y conjugate of j omega is equal to minus infinity to plus infinity, and this x conjugate and conjugate is x, and e to the minus j omega t conjugate is plus e to the plus j omega t. Right? So what do I have here? This integral. What is this equal to? Is this the Fourier transform of x? Or related somehow to the Fourier transform of x? No, okay. I mean, it is related, yes. right? The exponential must be negative, right? So can I then therefore relate it somehow? I mean, do some manipulation in x of j omega so that that thing becomes equal to what this integral is, right? And right, it's minus, right? Excellent, right? So this is x of minus j omega, right? If I just replace omega with minus omega, right, I get x of minus. So this is really x of minus j omega, right? And as a result, the conclusion we have here is that y conjugate of j omega is equal to x of minus j omega, and this implies that y of j omega is equal to x conjugate of minus j omega, right? More or less the same, actually exactly the same methodology we used for Fourier series. Now, based on the same set of ideas, so in other words, when you take the conjugation in the time domain, what happens in the frequency domain is that the Fourier transform is conjugated and is flipped. So there are two things that go on because of conjugation in the time domain. The Fourier transform is conjugated and flipped, right? So there are two things that go on. Now, there are several implications that we could draw from this, or inferences we could draw from this, as just like we did in the Fourier series. So if x of t is real, and I'm not going to go through those proof, I'm just going to give you the results because they're very similar to what we've done already. If x of t is real, what do you think? X क्या satisfy करना चाहिए x of j omega को? कोई मुझे unmute करके Hamza Rashid, so I can mark you down as well, right?
Sir, I'm not really sure. Like in x conjugate of j omega.
Yeah, so if x of t is real, तो x of j omega क्या property satisfy करेगा? Okay, Asad Baraich.
So I think जैसे Fourier series में किया था तो they will be conjugate symmetric.
Conjugate symmetric, excellent, right? So you can go through exactly the same process to find out kg x of j omega must be equal to x conjugate of minus j omega, right? So that must be satisfied. They're conjugate symmetric, right? X of t is real, then the Fourier transform is conjugate symmetric. Now I claim that if x of t is real, then I only need to specify the Fourier transform for positive frequency. In other words, if I specify the Fourier transform only for positive frequencies, that is a complete characterization of the Fourier transform. I don't really need to bother about the negative frequencies representation or depiction. Why do you think that is? So as you would have seen, perhaps, hopefully, on LMS as well, I posted an article, or wrote an article, and then I said, you observe the Fourier transform I've specified only for the positive frequencies. Can you guess why? Right? This is the answer to that why. Right? So why I claim that real signals के लिए Fourier transform जब भी मैं specify करूँगा, तो then it's enough for me to specify the Fourier transform only on the positive side of things, right? ये काफी है बस. This is enough. Or the specifying on the positive omega axis is enough. Why? Kyori, what do you think? Why is that enough? Given x of j omega for positive frequencies, would I be able to determine x of j omega at negative frequencies? Yes, right? Because I know that if I know what x of plus j omega is, I know what x of minus j omega is, because that's just a conjugate of what it was for the positive frequencies, right? So therefore, specifying it for the negative frequencies does not really add any additional information, right? Because I know there's a relationship between the two. And that's why for real signals, we often just illustrate or display the Fourier transform only for positive frequencies or not for the negative frequencies. Okay, because there's a relationship between the two. Okay. And then I can go on and go through the rounds. Okay, if what happens if x of t is real and x of t is even, what happens then? In that case, x of j omega turns out to be equal to... जी कौन बोला था? Please go ahead.
सर आपने मेरा नाम लिया है?
नहीं निया लिए लेकिन आप बोलते हैं
नहीं सर वो आई एम सॉरी वो आपने बोला ना व्हाट हैपेंस देन तो मुझे लगा कि आपने मेरा नाम लिया
चलें what happens then अब बोल दिए जी
सर आपको कोएफिशिएंट्स के लिए पूछने से वो मैं बता सकता हूं
if x of t is real and x of t is even, the Fourier transform is real, right? X of j omega is equal to x conjugate of j omega, right? So it's real,
just like the coefficients,
just like the Fourier series coefficients. At the same time, if x of t is real and x of t is odd, फिर क्या होगा?
So imaginary होगा,
right? So then in that case, x of j omega is going to be equal to minus x conjugate of j omega, and that just means that the real part is 0. Or another case, purely imaginary. This is purely imaginary. Okay, I mean everything that we did for the Fourier series, I mean that carries on a straightforward fashion to Fourier transform as well. Okay, the same methodologies. All right. Now, जी उमर.
फिर इसमें वही फिर Fourier series वाला question raise होता है कि is the inverse also true? If we are given this about the Fourier transform, can we say something about the signal itself?
Right. So excellent. Right. So if you're, for example, given the fact that the Fourier transform is real, is there a guarantee that the time domain signal is going to be real? And even the answer is no. Right. Just like we discussed on the discussion board as well. Right. The answer is no. But what is necessary is that the time domain signal would actually be conjugate symmetric. Okay? And real and even signals are a subclass of conjugate symmetric signals, or the category of conjugate symmetrics. Okay? So it may not be. So there's a forward implication. However, on the other hand, if I say if the Fourier transform is real and is even, then there should be a guarantee that the time domain signal is real and even as well. And think about that. Okay, so I'll let you think about this on your own, right? And then I can answer questions if you have. All right. So by the way, just a complex number question here. From here, x of j omega, if that is equal to x of j omega minus j omega, that implies that the absolute value is even, right? As a function of omega, that's an even function or an even signal if with omega as the independent variable. And that's also, and the phase of x of j omega is odd, right? So let me leave this off as an exercise as well to some basic complex number analysis. Okay.
ये आपने यानी originally it is if x of t is real, then x of j omega is equal to conjugate of minus j omega, right?
Yeah.
आपने उस बाद में क्या किया आपने ये written x conjugate of j omega simply.
Right, so this is minus this is x conjugate of minus j omega.
Okay.
Okay. I mean, this first condition implies that the magnitude is even, and the phase is odd. Okay, so I'll let you do it yourself. All right, so here's the next property, which is, differentiation and integration. So this is where things might be a little confusing. Okay. So let's discuss differentiation first, right? So if x of t has a Fourier transform x of j omega, the question is, what is the Fourier transform of the derivative of x? Right? And I'm not sure how many of you tried the end of chapter problems. There's at least one student. There is exactly one student who approached me and asked me a question. Okay, there's a problem, शुरू में basic problems है chapter 3 के end में, which is exactly this. कि जी for periodic signal है उसका मैं derivative अगर ले लेता हूँ, तो what happens to the Fourier series coefficients? And he asked me, यार ये किस तरह करूँ मैं? Did any one of you do that on your own? End of chapter problems. Right, so end of chapter problems are necessary for you to do. I mean, if you really want to prepare, right? So what homeworks are the bare minimum, right? Or uske upar end of chapter problems, supplemental information, right? So this is and basic end of chapter problem at the end of chapter 3, which is related to this. The question, let's try to unfold this. Iska matlab kya hai? Or what would y of j omega be? So far, the answers that I'm seeing, not exactly true. Right? Talha, why do you say this? X of j omega minus x of 0?
ये क्लास में इसी तरह होता है ना. I'm not exactly sure, लेकिन जिस तरह के क्लास में होता है, क्लास डोमेन में जब हम जाते हैं, d over dt x of t में, you have this problem, ये differentiation property.
Right. So Laplace में exactly ये नहीं होता. Laplace there's an s multiplied by. Right, and the Laplace that you have studied is a one-sided Laplace transform. That's why you have an x of 0 there. Otherwise, that x of 0 should not be there. Two-sided Laplace, right? So the answer is similar, right? The answer is similar with some changes because we're integrating on both sides from minus infinity to plus infinity. Okay. The integral does not cancel out. So Swan, why do you think the integral cancel out? I mean, this is not, when you take the derivative, there's no guarantee that after you take the derivative, the signal is going to be something which cancels.
अगर हम synthesis equation ही लें तो उसमें अगर x of t है और तो साइड में इंटीग्रल आता है 1/2 पाई के साथ, तो दोनों साइड पे अगर हम डेरिवेटिव ले लें तो लेफ्ट हैंड साइड पे डेरिवेटिव ऑफ x of t आ जाएगा, तो राइट में क्या वो कैंसिल नहीं हो जाएगा d of t के इंटीग्रल के साथ?
No. नहीं, so that does not happen because you have to सबसे पहली बात है कि जो synthesis equation है उसमें integral is respect to omega, not respect to t.
Yes.
Right?
Yes.
So
yes,
that doesn't apply, right? So here's the as you said, let me write down the synthesis equation, right? So x of t is 1/2 pi integral from minus infinity to plus infinity, and this is x of j omega and e raised to power j omega t, and this integral is with respect to omega. Okay? But yes, you're right, Kiji. This is what you, this is the starting point. And let me differentiate both sides with respect to t as you suggested, right? So I differentiate this with respect to t. So I'm using another color here, right? So I differentiate this with respect to t, and I differentiate this with respect to t, and see what happens. So what do we get on the right-hand side, therefore?
So e over j omega t, I guess, with respect to t over.
Right. So the 1/2 pi is a constant, right? And integral is respect to omega. So therefore, the derivative can go inside the integral, right? So it can go inside, and apply where? The only thing that's a function of t in this entire expression is this thing here, right? And therefore I can say, yeah, this is actually equal to integral from minus infinity to plus infinity x of j omega, and here is where I have the derivative of what? Of e raised to power j omega t, right? So this is what I differentiate, and then the integral is with respect to omega, right? So that उसमें कोई फर्क नहीं पड़ता, right? So Abdullah, y multiplied by 1 upon j omega, derivative में what happens with the derivative? So this is 1
Oh, sorry, sir. Divide हो जाएगा.
Right, so it's multiplied by j omega, right? That's, I think, what you wanted to say. Right, so this is x of j omega times j omega times e raised by j omega t times d omega. Right, so this is 1 upon 2 pi, and this integral is from minus infinity to plus infinity. This is j omega, and then this is x of j omega times e raised to power j omega t d omega, and this is equal to the derivative of x. Right? So if I look at the right-hand side, right? If I look at the right-hand side, what is the right-hand side the inverse Fourier transform of? Right? I see that this is what the right-hand side is the inverse Fourier transform of. Right? And therefore, this right-hand side is really the inverse Fourier transform of what? Of what j omega times x of j omega. And from here, I conclude that the Fourier transform for the derivative of x of t is just simply equal to j omega times x of j omega. Right? A nice and elegant result. Okay. All right. Does it make sense? I mean, why do you multiply it by j omega? Intuitively, chale, is kar lete hain. Right? Now you can once again work with cosines. Right? If you take the derivative of a cosine, right, the cosine omega naught t, the omega naught is going to come out, right? If you differentiate with respect to t, it's cosine omega naught t, they differentiate that, the omega naught is going to come out, right? So that slope depends on what the frequency is, and is actually that slope or the derivative is proportional to the frequency. The higher the frequency, higher the derivative, right? Or in other words, derivative is just a rate of change, right? If the frequency is much, much higher, higher the rate of change. Right? And this makes sense over here as well, right? So when you take the derivative of that, the higher frequency components are going to be amplified more than the lower frequency components, right? And the phase changes as well, right? So because the J actually changes the phase, right? Which is exactly excellent at the point, Abdullah, as well, because sine becomes a cosine, right? And the phase changes, and that's what the J does to you, right? So the phase is changed by 90 degrees. Right? So everything is that's the intuitive explanation of what the derivative does to your time domain signal. When you take the derivative of the time domain signal, the high frequency components are amplified more than the low frequency components. That's essentially what the derivative does. Okay? Now here's the question, K. We've been able to figure out, this is the relationship. This is what happens when you take the derivative. What happens when you take the integral? फिर क्या होगा? In other words, what I am trying to say is, KG, if y of t is another signal which is given as the integral from minus infinity to t of x of tau d tau, the question I want to ask is here, what is y of j omega as a function of x of j omega. And Asad and Umar and Daniel, all of them say you just divide by j omega, right? So why do you think, Daniel, divide by j omega? It's just the inverse, right? Is that what you're saying there?
Yes, sir. वैसे भी sir integration करेंगे जब उसकी.
Yeah, so it's just the, because the derivative is just the inverse operation of the integral, right? So if I differentiate both sides, what I get is dy by dt equals, so let me, dy of t divided by dt, that's equal to x of t, right? And if I compute the Fourier transform, therefore, that means that j, or in other words, x of j omega, so j omega times y of j omega must be equal to x of j omega, and therefore this implies that y of j omega should be equal to 1 upon j omega times x of j omega. So just the inverse operation. Derivative just multiplies with j omega in the frequency domain. Integral does the opposite, just divides by j omega, right? Now, this result turns out is not entirely correct. This result is not entirely correct. There's a small bit of a nuance here that we're missing. Can anybody guess here what that nuance is?
So when omega is 0?
When omega is 0. Excellent. कौन बोला था? Sorry.
Abdullah.
Abdullah. क्यों Abdullah? What do you think? Why is that an exception? Or
सर डिनोमिनेटर में 0 आ जाएगा ना, तो वो infinity पे चला जाएगा.
Right. So that's one way to think about this. I would think about it another way, which is KG, देखें, x of j omega is equal to j omega times y of j omega. That means x of j omega evaluated at omega equals 0 is 0. Right? So the y की value omega equals 0 पे है, वो किसी भी सूरत आप extract नहीं कर पाएंगे. Right? Because when you multiply anything with a 0, that process is non-invertible. Right? In general, when you multiply anything with a function with a constant, that process is invertible in the sense you can just divide by that number that you are multiplying with, except when you're multiplying is the number 0, right? Because when you multiply anything with 0, there's no way you can get it back. There's no way you can invert it, right? Because there's a many to one mapping, right? So omega equals 0 becomes a problem, right? So y of 0 is not necessarily known in this case, right? So that's a slight bit of a nuance that we need to cater for. Another way to think about this is, okay, what if there was another signal y1 of t, which was equal to this integral minus infinity to t, x of tau d tau, plus some constant, right? And this is probably something we're already aware of. Okay, integrals mein those constants or differentials mein, I mean, those constants are something we need to determine separately, right? In this case, we find out that dy1 of t divided by dt turns out to be equal to x of t once again, right? And therefore, we say that y1 of j omega, in this case, turns out to be equal to 1 upon j omega, x of j omega, which in this case turns out to be the same as y of j omega. Right? Even though, and that's important, even though y1 of t was not equal to y of t, and that cannot be because the Fourier transform has to be a one-on-one mapping, right? So there's this constant that we need to cater to, and this is to cater for. And the problem precisely is at omega equals 0, right? So what is the final verdict then? This is something that I am not going to prove, but rather state. And so So it turns out that y of integral minus infinity to t x of tau d tau, the Fourier transform for that is indeed 1 upon j omega times x of j omega. But then there's a term that only exists at omega equals 0, because omega equals 0 was a problem, right? And that turns out to be, without the proof, I'm not giving you the proof, is equal to what x was at frequency 0 times delta of omega. Okay, so the signal that you're integrating, uska koi na koi DC component residing in omega equals 0. That actually contributes to an impulse residing at omega equals 0 in the frequency domain, right? So if there's no DC component in x of t, then the 1 upon j omega times x of j omega holds true. That holds true. Okay? And once again, I'm going to state this again. This is a result that I am stating without a proof, right? The proof is perhaps not available in the textbook either, but you will be able to find the proofs in other resources. Okay, so we're going to state this as a fact, or take this as a fact. Okay, and just the last thing that we're going to do in the class today is just apply this integration property to find the Fourier transform of the unit step function. How can we use, first of all, is u of t absolutely integrable? No. Okay, good. Right, so इसका मतलब इसका Fourier transform converge नहीं करना चाहिए, right? That's something we know. But then we see perhaps there's something we can do with some using some deltas to be able to specify this, and it turns out yes, you can, right? The next question is, how can I use the integration properties? There are other methods of finding the Fourier transform for this in terms of delta function, but how can I use the integration property to find what I'm looking for? Any ideas? What is the Fourier transform of u of t? How can I relate u of t to be an integral something?
Sir, u of t is an integral of delta function.
Excellent, right? So u of t is actually the integral minus infinity to t of the delta function, right? And then just applying the integration property, what I get is u of j omega is equal to 1 upon j omega and the Fourier transform of x. What is the Fourier transform of x? Right, so let's do this here. So that x of t equals delta of t, and therefore what is x of j omega? Is 1. Good. X of j omega is 1. So this is x of j omega. Let me write down the property itself. This is times x of 0 times delta of omega. And therefore, this is 1 upon j omega times 1 plus pi times delta of omega. Right, so this is the Fourier transform of the unit impulse or the unit step. All right, let me just leave the following as an exercise. We may solve this in the next class as well. But something for you to think about. Determine the Fourier transform of the following signal x of t, and the x of t looks like this. This is t. This is x of t, and the signal is 0 everywhere at -1. There's a discontinuity and then sort of a ramp and then goes back. And the height here is -1 and the height here is +1, right? So essentially what I'm saying is that the x of t equals t for absolute value of t is less than 1 and is 0 otherwise. Now, one of the ways you can do the Fourier transform is just plug this into the synthesis equation or the analysis equation. Find the inverse Fourier transform. You'll have to do, I believe, integration by parts here. Okay? And that's something you can do. Go ahead and try it out. There's another way to do it, and that is through the integration property, which we're going to do in the next class. So may I request that you try to do this by integration by parts and find out what the answer is. And the next class, we're going to try to apply the integration property and see what answer we get. Okay. Ji Hamza, you have a question.
सर पिछली एग्जांपल में हमें किस तरह पता लग रहा है कि डीसी वैल्यू नॉन जीरो है?
किस चीज की? एक्स की?
सर यू ऑफ जे ओमेगा जो हमने अपना फाइनल आंसर निकाला है, इसमें आपने साथ में लिखा हुआ है पाई टाइम्स डेल्टा ऑफ ओमेगा। तो सर ये हमें किस तरह पता लगा कि डीसी वैल्यू नॉन जीरो है? किस तरह
पता चला? और यू वांट टू मेक सेंस ऑफ के ये क्यों है? देखिए किस तरह पता चला, वो तो आई जस्ट अप्लाइड द इंटीग्रेशन प्रॉपर्टी, राइट? सो आई जस्ट अप्लाई दिस इंटीग्रेशन प्रॉपर्टी हियर, right? There's a delta of omega here, and multiplied with delta of omega is what the DC value of x of 0 was. And the DC value of x of 0 is equal to 1, right? So therefore, this becomes this. ठीक है? इसमें तो कोई प्रॉब्लम नहीं है, हमजा?
जी जी.
Right? Now, the next question is, why is the DC value, does it have a delta there? Or in other words, why is it equal to infinity? Right? So what is a DC value? सबसे पहली बात ये है, क्या ख्याल है? So what is u or x of 0 for that matter? If I say if somebody tells you, yeah, there's an x of 0, or the DC value which is the Fourier transform evaluated to omega equals 0, इसका मतलब क्या है? DC value का मतलब क्या होता है?
सर जो हमारे ए केस होता है, ए 0 पे सर जो वैल्यू आती थी, वो हम डीसी वैल्यू कहते थे ना?
हाँ, लेकिन वो असल में टाइम डोमेन सिग्नल की क्या वैल्यू, वो हमने सिग्नल्स क्लिनिक में वो एरिया अंडर द कर्व निकाला था, राइट?
जी जी.
Right? So, I mean, what did that represent? That represented the area under the curve, right? Over one period.
जी.
Right? But in this case, what is x of j omega? If I just look at what the Fourier transform relationship, just look at the transformation or the definition. This is x of t e raised to minus j omega t dt. What would x of 0 be? Capital X of 0 be? That would just replace
omega is,
and that's just x of t. तो पूरा x of t ले, from minus infinity to plus infinity, find the area of the curve for that x of t.
ठीक है सर.
That's the DC value. And now just look at u of t. U of t क्या है? उसकी आप DC value compute करेंगे, that will turn out to be infinity.
ठीक है सर.
Because it's not, I mean, it says an infinite area under the curve.
ठीक है सर. जब इंटीग्रल हम ले रहे हैं, इस एग्जांपल जो आपने कराई है, उसमें डेल्टा ऑफ टी का एरिया 1 होता है, तो इसलिए फिर आपने लिखी है. ठीक है सर.
Yes.
ठीक है.
Right. Any other questions?